Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This subject is the first paper in the first semester of the course. This lecture is the 55th lecture in the series. This part of the series we are discussing about the digital electronics. In the last lecture, we have learnt how electronic circuits are designed for the different gates, and also we have got an idea about how the gates are incorporated in the ICs, integrated chips. This lecture is devoted for getting some basic ideas about the simplification of binary expressions or the Boolean expressions. So, we are going to learn about what is Boolean algebra and the theorems related to Boolean algebra in this lecture. Let us have a look at the session outline of today's lecture. In this lecture, we are going to see a special gate called XOR gate, and also we are going to learn about the Boolean algebra. Under that, we are going to learn about the De Morgan's theorems and few logical expressions. First, we will see one special logical operation. If you bring it to your mind, in one of the earlier lectures, I have given a list of logical operations available, starting from the not, or, and, like that. I have mentioned one logical operation called XOR. It means exclusive OR. So, I would like to highlight about the operation called XOR operation, and after learning about that, we will go ahead with the Boolean algebra and the expressions related to logical statements. Let us now have a look at the special operation called XOR operation. The XOR gate has an output 1 only when the inputs are complement to each other. The Boolean expression to represent the XOR operation is given like this: y is the output. This part of the output has a complement for only b, and this part has the complement only for a. So, the meaning is either a or b, because this is a OR operation. The complement should be a complement to have an output as a high value. Instead of showing this lengthy expression, we have this one single symbol which represents the exclusive OR operation. A plus sign with a circle is a symbol for XOR operation. Where this XOR operation is used? In the circuit simplifications, this XOR is very much used, and also when the binary symbols are transmitted, when the digital signals are transmitted, to check whether the received signal is correct or not, we will use one digit for checking that. It is called a parity digit. We will check that with the parity digit whether the signal is a correct signal or not. So, for that purpose we will use this XOR operation. When we come across the digital communication, at that time the XOR operation will be very much useful. So, I thought it is worth mentioning the XOR operation in this series of lectures. So, let us see how the XOR gate is represented in electronic circuits. The truth table of XOR gate is given here. If A and B are either at low state or at high state together, then the output is at a low state, there is no output. The output is high only when either A or B alone are high. So, that is how the OR XOR is explained. So, here it is shown either A or B should be high to have an output high for the XOR gate. The circuit symbol is typically like this. We have one curved line at the input along with the OR gate. This is a OR gate. With the OR gate we put one curved line at the input stage, then it is a XOR gate. We are understanding the operation of each logic gate with a circuit also, an electrical circuit with a lamp or the bulb connected to the circuit. If the bulb glows, then it is representing a high state. If the bulb does not glow, then it is representing a low state. So, we are using switches. We have even represented all the basic gates with simple switches. Here also, how a switch is used for showing the XOR gate. Let us have a look at the circuit connections. Here we have a switch, a special switch which has the terminals A and B, but only A or only B will be maintained at a high state. If A is maintained at a high state, B is automatically at a low state, and similarly when B is maintained at a high state, then A is maintained at a low state simultaneously. So, that takes care of the middle part of the truth table represented here. So, only at that condition we will have the output in the circuit will glow. So, that is how it is represented. If both are connected here with 1 and 1, the circuit, the current will only flow through this circuit, and then the output will not, because itself will form a loop. The current to the bulb will be 0 when both are connected to the switch. So, it is a typical switch representing the XOR operation. So, this will be useful at a later stage for us when we take up the logical expressions for simplification. Now, it is time for us to learn about some of the basic logical expressions. What will be there in the logical expression? All the logical operations we have come across will be there in the logical expressions. We are restricting ourselves in this discussion with only two variables, A and B, with two inputs. When we learn about the digital electronics alone as a separate subject, we will be able to take up for our discussion more than two inputs, the 3 input, 4 input gates also. They are also available in the form of ICs. The circuits are already designed, but for our basic understanding we are taking only the 2 input gates. What is a logical expression? It contains logical operations in it connecting the logical variables, namely here the A and B. To handle the logical expressions, we have to equip ourselves with the algebra called Boolean algebra. I have given a brief of Boolean algebra when we have come across the different number systems used in the digital electronics. The binary number system we have taken up. There we have come across the term called Boolean algebra. So, let us see what is Boolean algebra. In Boolean algebra, we will be using mainly the two theorems. We have lots of theorems, but these theorems are the fundamental theorems. They are called the De Morgan's theorems. The two De Morgan's theorems are very important in dealing with NOR and NAND gates. They state that a NOR gate that performs this a plus b whole complement function is equivalent to a complement and a b complement. We will have a look at the typical expression, but let us read out the statements because it is given as the theorems. Similarly, a NAND gate that performs a dot b, the whole complement function, is equivalent to the a complement or b complement. The De Morgan's theorem, basic theorems, mainly deal with the two combinational gates which we have learnt, NOR and NAND gates. A NOR gate and NAND gate could have the other forms also when we represent them. That is what is the whole about De Morgan's theorem. So, let us have a look at the De Morgan's theorem in equation form. The first theorem is this: the complement of OR is equal to the AND of the complements. So, this is the other way of stating the first theorem. The complement of OR is given on the left hand side, and the AND of the complements, individually the complements are taken and it is ANDed. A complement is ANDed with the B complement. These are some of the terminologies we come across while learning the De Morgan's theorem and logical expressions. The second theorem, the complement of AND equals the OR of the complements. So, this is the complement of AND, which is nothing but the NAND, is equal to the A complement ORed with the B complement. So, individually the complements are odd here, together the complement is taken for AND. So, two theorems are to be proved. We need to understand the two theorems so that these theorems could be used in simplifying the logical expressions. What for we need to learn the theorems? Ultimately, we should be able to design logical circuits with the gates for any given logic expression. So, that is the core idea of the concepts of Boolean algebra. Let us learn further about the De Morgan's theorem. The theorem can be proved by considering the two variable cases and then extending the result. I will be able to take up the proof for the De Morgan's theorems after a short break. Welcome back. We are discussing about the De Morgan's theorems. I will have to give the proof for the two De Morgan's theorems, the first theorem and the second theorem. We are not going to use any big circuit for giving the proof. We will just form a truth table for the NAND NOR gates and of course for the complements of the inputs, and then have a look at the outputs to see the two De Morgan statements or the theorems are true. So, let us have a look at the proof for De Morgan's theorems. The theorems can be proved first by considering the two variable cases, namely A and B, and then extending this result. See here, the truth table is formed for A and B, two inputs. The usual combinational input is represented here. Their individual complements, the A complement and B complement, are also given. The remaining 4 data are involving the De Morgan's theorem. The NAND operation A dot B whole complement, when we take, this is the output that could be easily taken from the inputs that we have for A and B here, and then this A dot B whole complement is equal to the A complement or B complement, that expression. So, when we take the output for this expression from the truth table, we get this. So, when we compare the two expressions, both are the De Morgan's first theorem. So, the outputs are same. So, De Morgan's first theorem is proved. Similarly, the last two columns, the A plus B the whole bar, here the plus is or, that we have to keep in mind. A plus B the whole bar, for that we take the output, and the output for A complement and B complement, for that expression when we take, these two outputs are same. So, this proves the second theorem. From the truth table, we could very easily prove the two De Morgan's theorems. These two De Morgan's theorems are very much useful for simplifying the logical expressions. We will devote one full lecture for simplifying the logical expressions. We will take some examples for various logical expressions, how these De Morgan's theorems would be very useful in simplifying them, we will learn in the lecture. Now, it is time for us to have a look at the other logical expressions and the standard results, or we call them as logical identities. So, let us familiarize ourselves with some of these identities. Boolean algebra, named after a mathematician George Boole, is the algebra of logic, which is applied to the operations of computer devices. The rules of this algebra is simple, speed and accurate. This algebra is helpful in simplifying the complicated logical expressions. Keep one point in mind, the Boolean algebra deals with only two variables, zeros and ones. Some of the functions that we have in Boolean algebra, the laws, we will have to learn now. So, let us learn some of the basic laws that we have in Boolean algebra. The fundamental laws of Boolean algebra are given below, which are necessary for manipulating different Boolean expressions. So, let us have a look at the slide to know more about the laws available under Boolean algebra, the basic laws. Boolean algebra has this commutative law, which holds good for the OR operation and also the AND operation. The OR operation is represented by the plus symbol here, and for AND operation normally we will have to use a dot, but as I have mentioned in one of the earlier lectures, the dot is normally dropped, which is not normally used. So, this is the commutative law, A plus B is equal to B plus A. Similarly, AB is equal to BA. The commutative laws for OR operation and AND operation hold good for the Boolean algebra. What are the other laws that we have? We have the associative law and distributive laws for the variables A and B. So, let us have a look at the two laws. This is associative law, A plus B plus C in bracket is equal to A plus B in bracket plus C. This is for the associative law for OR operation. Similarly, we have the associative law for AND operation also. A, B, C within bracket is equal to AB within bracket C. And this is the distributive law. A B plus C within bracket is equal to AB plus AC. In normal algebra, we have these three laws for simplifying the expressions: commutative law, associative law and distributive law. In the case of logical expressions also, or in Boolean algebra, these three laws very much hold good. We will now learn about some of the basic logical identities that are available under Boolean algebra. These are some of the basic operations. I would like to call them as the logical identities. These involve only one variable A. I have tabulated them according to the kind of operation. This section shows all the operations involving OR, and this section shows all the operations involving AND. And this is also a very important expression. So, one by one let me explain. The A variable or ORed with 0 is A, the A plus 1 is 1, A plus A is A plus A complement is 1. Similarly, A dot 0 is 0, A dot 1 is A dot A is A dot A complement is 0. Here the dots represent AND operation, the plus signs represent OR operation that we have to keep in mind. This is a very peculiar equivalent. The complement of complement is the variable itself. A complement of complement is A itself. So, this also is very much useful in simplifying the logical expressions. How in normal algebra the number 1, the numerical value 1 is called as the multiplicative identity. When we multiply any variable with 1, the result is that number itself. So, it is called the multiplicative identity. Like that we have lots of additive identity, 0 is the additive identity, like that. So, the expressions just now we have seen in the Boolean algebra are also identities. They have their own specific outputs. They come across in the simplification techniques very much. There are some other results which would also be very much useful in simplifying the logical expressions. Let us see them also. These are some of the basic theorems. Already we have learnt about the two theorems, De Morgan's first theorem and second theorem. These theorems are also very useful. I would like to just highlight about one or two theorems. The A plus AB is equal to A itself. Here what we can do is, because of the associative property, the A could be taken common. Once A is taken common, it will become A within bracket 1 plus B. 1 plus B is 1 itself. Again A dot 1 is A itself. So, this is how we can explain each expression, but the results are very important. So, I would like to just show the results as theorems. So, wherever we come across these forms, directly the results could be used. The proof for these theorems are not discussed because it is a time consuming but simple theorems only, but it will be consuming lot of time. So, I would like to just show the highlights of these theorems. Maybe for one or two we can see the proof, but for the remaining without proof we can take them as theorems as such. Let us have a look at the theorems one more time. So, whenever we come across these kind of expressions in logical expressions as a part, then they could be simplified as the expressions shown on the right hand side of the expressions shown here. The proof for these theorems are not, as I said, exhaustively given. Theorems involving a single variable can be proved by considering every possible value of the variable. For example, this A plus 0 is equal to A could be proved by considering A as 0, in that case output is 0. Similarly, A as 1, the output is again A, which is considered as 1 here. So, like that we can take up different values for A and B and prove these theorems. It will be boring also when we try to prove all the theorems. So, I just wanted to show one or two theorems and their proofs. Let us take a two variable expression. The theorem involving this two variable A plus AB is equal to A is also proved using a simple truth table here. See, we take A with all the possible combinational inputs and the AB is taken. A plus AB is this one. So, this expression is compared with the A input, both are the same. So, this statement is true. So, like that these expressions which we have seen just now are very much useful. They become very handy when we simplify logical expressions. We will see some of the simplifications and the techniques used with some examples in the forthcoming lectures. It is time for us to see today's session summary. In this session, we have seen one special gate called XOR gate, also the Boolean algebra, the De Morgan's theorem and some of the logical expressions. Let us test our understanding by answering these questions. Explain the logical operation XOR. State and prove two De Morgan's theorems. State and prove the commutative, associative and distributive laws in Boolean algebra for two variables. Give few logical identities. With this, I would like to wind up this lecture and see you again in the next lecture with some of the examples for simplifying logical expressions. Thank you for listening.